So next up, we have Reuben R. George and Mahesh Venkataraman from Accenture Solutions, and they would be talking about continuous system reliability management. Over to you.
Hello, everyone. Thank you for the opportunity to share my thoughts on continuous system reliability management. Good morning, good evening to all those who have joined today. It's a pleasure to talk about this topic because it's close to my heart. I've been working on this for more than a decade now on performance and reliability, and the thoughts that I'm going to share with you on this topic are basically my experience working with innumerable number of customers during my tenure here at Accenture. So let me get straight into it. Now, we are very familiar with system quality attributes. And what I put up there on the screen are a bunch of those attributes. Now, you may be familiar with few of them, but with respect to keeping a system up and running for a duration of time, some of the system quality attributes that I've highlighted on the screen becomes very important to use. For example, some of these quality attributes related to availability, fault tolerance, observability, safety, scalability, resilience, recoverability, reliability. And all of these system quality attributes have to be evaluated, monitored, managed, and continuously improved upon. Okay. So today my topic is about how you would be able to kind of integrate all these quality attributes and create some sort of framework. So I won't tell you how the framework would look like and how do you build the framework, but I will tell you all the components that become part of this framework, and how do you structure your thought process, your strategy towards building continuous reliable systems. Okay. Now, it's not going to be a bunch of tools, but I'm going to talk about how do you bring in multiple thought processes, tools, processes together to achieve this goal of system reliability. Now, just to give you a kind of a quick gyan on this topic, first and foremost, you have to understand reliability is a measurement. It is not. It's the one property of the system. It's actually a measurement of a property called resilience. And resilience is the actual system property that we are wanting to improve upon. It's a system attribute that we want to improve upon with respect to fault tolerance, high availability, and recoverability, and so on. So reliability is the measurement, and one of the metrics that we use is availability. But if you notice, I've put two other system attributes on the sides. One is the observability. It's again a system property on an attribute that helps you to understand what's happening in the system, in the stack, in the architecture. And higher the system is observable, the more the system is observable, the more you're able to answer questions when certain events occur. On the right side is the science part of it, and is the science attribute for system quality and system quality attributes is the science part. The science part includes a lot of philosophy also involved in it. It's built on philosophy, processes, and principles. And safety, so all of the system reliability and system resilience topics and attributes come under software safety, system safety. And so actually many of these what I'm going to talk to you in the coming slides actually kind of are picked up from software safety approaches. And these software safety approaches have been a well-established discipline since the 60s. And we see them even more relevant today as we're building very sophisticated cloud machines today. We are looking at scenarios where we are deploying applications, we are deploying our workloads to public, private clouds, we're doing hybrid clouds, we're doing multi-clouds, we're doing it on microservices, and all our network functions are virtualized today. So we are bringing in a lot of complexity into our deployments, and hence reliability is of the most paramount concern. Okay, and one thing that we have, I just put this up there is just to give you that a downtime can be caused internally. You could have it as an internal fault or an external fault. Now, based on our research and what we have seen in the past 1 year, in the year 2021 itself, we've noticed that there is one major cloud outage happening every 2 weeks. And these are for not talking about secondary hyperscalers. We're talking about primary hyperscalers like AWS, Google, Azure, even CDNs like Cloudflare, even certificate authorities like Let's Encrypt and so on. So we are seeing downtimes happening on our service providers, even our SaaS platforms. Many of them, Slack, GitHub, GitLab, and Salesforce, and so on, have outages which actually disrupt our businesses. But as we are entirely dependent on them, it's important that we harden our systems against such faults, either external and internal. And we've also seen that the intangible cost because of a downtime is actually far outweigh, and it compounds the loss cost, tangible cost to a downtime. And it's important that we have our systems up and running and provide the best user experience, best customer experience. Yeah. And another thing that we do before we enter into more about these outages, that many of these failures are actually internal and also external, but those which are internal are classified here. This is a research from one of our partners. We work with them on hardening many of our customer systems, and we noticed that majority of the problems we face are infrastructure, service provider issues, configurational issues, and many of these things are something we can prevent if we had the right data, if we had put in right design patterns and practices into constructing and deploying our applications. So they are avoidable. That's what we're saying. It is avoidable if you have a good testing strategy. Now, the testing strategy has to be founded not on a tool, it should be founded on a process, because you would limit your testing strategy with the tool's capability. But we should be beyond the tool and be based on a process. So this is where I'm going to talk to you about how to enter into this whole topic of resilience testing before I jump into continuous resilience testing. Now, in resilience testing, the focus would be to understand the architecture. So we are not looking at just component level, but we are looking at the holistic global level architecture. And in traditionally, the role of resilience testing or some sort of availability testing or reliability testing was focused directly on the disaster recovery, network teams, and infrastructure teams. But today, it's become very imperative for us because as they all move to a software-based deployment, we quality engineers have to get ourselves hands dirty on these topics as well. So what used to be on a global level outage or failure in terms of failure testing in terms of disaster recovery has now, because of the advent of cloud and cloud service providers and tools that are now available, and the ability to kind of expose services that you can directly attack and so on. You would have now new vendors that have come up, new vendors that are able to help you kind of map out your system and help you do customized attacks. So from disaster recovery, now you've come to a state where you're doing chaos engineering or chaos testing and so on. Chaos testing have been predominantly around using tools to inject chaos, inject faults into the environment, into your component. But what I'd like to talk about here is a structured approach and how you even do chaos testing, and finally, how do you automate all of this activity so that you would harden your system continuously rather than waiting for a fault to occur. Now, to do this, there are three parts. There are four parts to it. The first part is to do a static assessment. It's kind of like creating a photograph or a snapshot of your environment. It could be you could extract that data from your architecture topology, and then able to map all the nodes and all dependencies between different systems, and then be able to and give a first cut and saying which are those systems that you could start with hardware level, you could go software, you could look at network, you could look at adapters, you could look at your streams, and then you create one view of how your architecture looks like. And many of you may have that view. And if you're part of a very small LOB, you could start with that smaller LOB and then see what are the upstream and downstream systems that talk to your LOB. Yeah. So one is to do a static analysis, is to identify potential points of failure in that static analysis review of your architecture. Now, how would you even do that? Is to start with the whole architecture. You could use many techniques in this. You could use failure mode analysis. You could do theoretic process analysis. So there are multiple techniques to do it. But the most simplest would be to look at the architecture as a whole, and then start breaking up your architecture, decomposing it into based on business flows. That would be the most ideal way of doing it, is to do it with business flows and all the technology components within that business flow. And then you zoom in onto those technology components and understand what is the exact what is the application that's running it, what's the software that's running it, what's the hardware that it's based on, and so on, and the network. And then from you create this kind of tree structure for that particular line of business, or a business flow, or a functional flow, and then go at the root, which is the lowest level software component, and then start your failure mode analysis. Okay, so your failure mode analysis would look like, what if, and you could break up your failure mode analysis into probably hardware, software, adapters, and virtualized software that you're running on top of it. Now you look at where it could go wrong, and what is its impact on upstream, downstream, how often this is going to happen based on looking at data from your monitoring tools. You look at also at you look at monitoring tools, you look at your incident data and see how often this happens. Then you identify what is the probability. You look at how easy it is to detect, and you also look at what's the severity, how many upstream, downstream are affected, how many dependencies are affected. But before I go straight into that, let me just clear up the rest of the stuff. So now when you come up with these failure modes, you understand how your architecture is behaving. You got to now what you get is a bunch of test scripts, or a test list that you could test script lists or scenarios that you would then go and perturb the system with. And that's when chaos testing tools comes in, and you use chaos testing tools. Now, chaos testing tools, you cannot just rely with gremlins and litmus chaos and chaos monkey and so on. You would have to look at even Windows system internal commands, because many times you would not be able to get access to all of these tools in your lower environments in on-prem, which is probably using AIX, Linux, and Solaris, and Windows machines. So for that case, you should now rely on system commands. And once you're able to harden your system on non-prod, you can push it into production. And that's where, and once you mature in this whole practice of hardening your system, you could even start trying out this hardening your system in production itself, rather than waiting to test it and validate it in the lower environment. And if you're able to automate all of this, is once you reach the state called this continuous resilience, wherein you're doing a lot of feedback from production through incident data, through tickets, through operations activities. You are now feeding back into this activity that the quality engineers are doing as part of resilience. Now, so I just want to give you a glimpse of how complex our modern architecture looks like. And as we're moving to cloud native, as we are moving our services to cloud, one thing that we have to also understand is decision making. Now, before we enter into chaos testing or any sort of resilience testing, we have to understand that the way we develop architecture today is basically 4 parts. First, we go with reference architectures. We have an architecture blueprint that we begin with, and how we have to kind of solve a industry problem or an industry use case. So we start with the reference architecture, look at best practices. All of the cloud vendors provide with well-architected frameworks that you could refer to understand what are the best practices to use. But then the next level just below that is to understand what are the services that are provided. Now, each of these services have innumerable number of combinations. And once these services, you've decided on the services, then the next question would be, how do you want the services to be configured? For example, if you're looking at compute and data and storage, you have different levels of configurations that you could apply on it now. And the lowest level is now, how do you configure your application itself? So let me the application itself. I'm just looking for a slide that I could share with you. Just a minute. Yeah. And it's where you apply resilient design patterns. Say, for example, how do you throttle your request? How do you apply circuits to your application? How do you apply bulkhead patterns? And these are various resilient design patterns that you apply to the application itself. So once you are kind of modeling and designing for resilience, this is what we would call as resilience by design. Now you got to validate this, and this is where chaos testing and testing tools are being used today for that part. So for resilience testing, this is the number of steps that we look at. This is the most simplified way of looking at it. It's you start with the architecture assessment, the static architecture assessment, wherein you identify failure modes, starting with the entire architecture, then going deep diving into each of those business flows, and then business flows to architecture components, which could be some technology that you're using. For example, if you're using something like a streaming media, like how we are doing right now with StreamYard, you're looking at transcoder, encoder systems. You're looking at caching. You're looking at database storage. So each of these different technologies that are used, you were probably using Kafka or something. So now you break it up into those components. Now you go one level deeper and see what is being used to deploy these applications, and then provide a failure mode analysis. And your typical failure mode analysis comprises of looking at where it could fail on the hardware, software level, and where it could fail as adapters, where it could fail on the virtual components as well. Now, and then that's where you do the experimentation. Now, we did this for a customer. The customer reached out to us to do assessment on the IT risk and resilience, and they had an RPO and RTO objective to achieve. And the approach that we did here is they were entering into chaos engineering or entering into resilience testing or resilience evaluation. They were not interested in hardening the system against data center level faults, where through geographical failures. So you're doing a disaster recovery kind of exercise. They've done that, but they don't want to kind of understand the state of resilience in their architecture. And this is the approach that we did. Um, for this, getting into the system, we had to get observability set up properly. Now, we looked at incident data, ticket data. We looked at application performance, application server logs, and we also look at services and network logs and so on. And what you get as first level of data that we extract as part of static assessment is that first column of text that you see. Is you kind of bring in what are the upstream systems, what are downstream interfaces, what are your usage patterns, and what are the failure patterns. And with incident data, we did a bit of sentiment analysis. With that, we are able to kind of structure our tickets and thread the tickets together to see kind of relationships between systems and the events that have caused the outages and so on. And the other thing that we do as part of our static assessment is also to understand where it could fail in terms of capacity as well. So those are the other viewpoints into the architecture that we bring in. And the next step to that is the fault chain analysis. You would call it as a lineage fault analysis or lineage fault graphs, or it has different names for it, wherein we kind of create these diagrams where we see that because of this failure, these are the upstreams that are affected, and these upstream failures are affected because they could in turn cause a chain of events that could trigger. And so we create that kind of analysis and that kind of a fault tree diagram, and then we then look at what are the second part is the where we look at each interface, what are those rate limits, throughputs, what are the usage patterns over the year, and so on. So that becomes one of the source of truth. And the final one is you're looking at availability and your SLOs and SLIs that the customer has already configured in. And if not, we work with them to do that. So those all of these data points or sources of data become your input to your failure mode analysis. So that you need to know if you're failing not because of a capacity problem or an application fault, or it's just a dependency fault. So and what you get as an output is a list of scripts that you use chaos testing for. So you don't just run chaos testing in the blind, but you're actually doing a very targeted, very heuristic based chaos testing or heuristic based resilience testing. And then you obviously you got to measure your resilience goals. This could be the time to recovery, time to detect, and so on. And you also look at your SLOs and so on. And what you get is kind of like a list of failure modes which could happen, places that where your system could fail, and then you kind of rank them based on risk priorities. And these risk priorities could be based on how probable they could be failing, how severe those failures are to its neighboring dependencies, and also how much of how easily it is to detect, either through manual testing or is it through an automated alerting mechanism that you've put in place to detect these failures. And with that you get is like a kind of like a descending order of risks based list of failures or failure modes, you could say, potential failures that you test against. And based on our kind of understanding, and it's become kind of like a rule of thumb, is if you solve for the top 40%, it kind of takes care of your system on the whole, because many of those are counterintuitive. So if you're fixing the top 40 issues, it could kind of fix the entire system, and you'll be able to achieve those availability goals and targets you're looking for. And then after this exercises, you could revise this RPO and RTO targets. Now, you may wonder, right, this is something that AWS is giving today or GCP is giving today. But however, as we move into cloud, we're looking at a multi-cloud continuum. So you cannot just leave to using some tools that work on AWS. You'll have to look at the multi-cloud continuum as well. Now, I just want to throw out some of the tools that we could use together. Some of these tools are used separately for their own purposes, in their own separate purposes. But if you are able to stitch this together, if in sort of like an automated fashion, you could achieve continuous resilience. Now, what is missing is what is missing in this is that data flow from your observability tools that triggers some sort of alert mechanisms that kind of categorizes your nodes into what kind of node it is, and then inject the specific fault to those architectural components and so on. So that kind of logic is something you got to build to achieve the fully continuous activity where it's hands-on, it's autonomous. But with this, you're able to achieve some bit of automation into this. And obviously, in any sort of continuous resilience testing, it is not just a quality engineer's point of view of just provide a solution that is fault tolerant, or to kind of validate, yes, this is fault tolerant release, but it's also important to also validate your operation teams. Because as we grow into SDETs and more of an SRE kind of role, this is where in operations teams data inputs, that's probably your run books, your remediation scripts have to be validated and tested for. And this approach kind of even validates even your remediation run books, your configurations that your configuration scripts through Ansible, Pulumi, or whichever tool you're using. You could be able to stitch that as well into this whole narrative. And this could be even your SRE approach, for example. Yeah. So these are my thoughts on continuous resilience. I'm open to questions on this topic. I try my best to answer you all. But I would leave you with this slide. This is something you could look at and get some ideas. If you feel that there is something beyond that we could explore, I'm always open. I think I missed one slide. It would have really been helpful, but I hope I was able to convey my thoughts clearly to you all. Thank you very much for your time.
Hi, Reuben. That was very insightful. You still have about 4 minutes if you want to go back and, talk about something. That'll be okay.
Sure. Yeah, I just wanted to go a little further into this slide. Is one thing that when we are designing for resilience is we have to keep in mind design trade-offs. What trade-offs are an important thing because patterns into the fray and affect your cost. So you would have to look at trade-offs, cost versus availability. If you think about it, it's important to look at cost versus availability, cost versus performance, reliability versus performance, and reliability, security versus reliability as well. So keep these trade-offs in mind because they would be helpful for you to kind of make those best decisions in hardening your system before even you do a testing itself. So your architects should keep these cost trade-offs in mind today. Now, some of these activities, coming back here to the slide where I want to talk about how could you even make this even continuous even further, is to kind of bring a feedback loop from operations, and that feedback could come as incident analysis. On the top, you could see what's missing over here as an element here is all of this is very familiar in terms of pattern analysis of logs and metrics analysis and so on. But one thing that's missing over here is incident analysis, incident patterns. And if you're able to stitch in incidents as well, and seeing patterns of usage based on incidents and those and because your instance brings in brings in the additional unknown parts, which is basically the black swan kind of events, which happen not quite often, but it does happen. But your system is kind of responding to those partial failures in a very in an unknown manner. So you could probably look at incident data and identify some of those black swans and gray swans kind of scenarios to kind of harden against even potentially those ones which are your outliers in your failure modes, outliers in your incident data, to then harden your system against probably those outliers may become your main problem in the future. So you could get that. One thing that's missing in this architecture is that incident data that you could use. So I hope that additional information will also be helpful for you today.